Hello everyone, my name is Charqui. I'm a PhD student at Qadiyat University. I would like to thank the organizers for accepting my presentation entitled Numerical Investigation of Surface Radiation Combined to Natural Convection Heat Transfer in an Open Cavity. In this presentation, we will start with an introduction, then we will describe the considered physical problem and the different equations of the adopted mathematical model. The numerical techniques used to solve these equations will be explained in the section Numerical Procedure. Then we will expose the main results obtained from the numerical simulations, and we will end with a conclusion. Natural convection flows in open cavities have attracted significant interest from scientific researchers and engineers during recent decades. This interest is dictated by the critical role played by this mode of heat transfer in many industrial applications. Examples include cooling of electronic components, aerospace engineering, heating and ventilation of buildings, heat exchangers, etc. In the present work, surface radiation coupled to natural convection in a square open cavity is briefly studied. The effects of two parameters that control the flow and heat transfer in such a configuration will be discussed, namely the Rayleigh number and the emissivity of the cavity walls. The studied configuration is represented in Figure 1. It's a two-dimensional square cavity opened on the right side and filled with air. The cavity is heated via its vertical wall, which is considered isothermal at temperature Th, while the rest of the walls is kept adiabatic. Beyond the opening, the ambient air is considered isothermal at temperature T infinity. By applying the principle of conservation on an elementary controlled volume, we obtain the following equations. Equation 1 represents the conservation of mass. Equations 2 and 3 represents the conservation of momentum along the x and y directions. Equation 4 represents the conservation of energy. The radiosity and net radiative heat flux equations are given by 5 and 6. Solving all these equations requires the knowledge of hydrodynamic and thermal boundary conditions. These conditions are given by equations 7 to 11. The finite volume method is used to discretize the equations of the mathematical model. The pressure-velocity coupling is solved by the simple algorithm. The power law scheme is adopted for convection diffusion coupling. A tridiagonal matrix algorithm is used to solve the system of algebraic equations line by line with an iterative procedure until the convergence criterion is satisfied. Let's now move on to the main part of this presentation. This figure shows the streamlines and isotherms obtained for different values of the Rayleigh number and for an emissivity equal to unity. For low Rayleigh numbers, the buoyancy force is still low. Thus, the flow structure keeps an almost symmetrical aspect to the horizontal median of the cavity. This symmetrical aspect is destroyed as the Rayleigh number increases and the streamlines become denser near the active and upper adiabatic walls. The isotherms show that a thermal boundary layer develops against the active wall, where a very significant temperature gradient occurs. Such a gradient becomes stronger by increasing the Rayleigh number. This is due to the reduction in the thickness of the thermal boundary layer. As a result, the fluid extracts more heat from the active wall. Figure 3 shows that the convective heat exchange increases rapidly with the Rayleigh number because of the intensification of natural convection with the difference between the active wall and the ambient air in terms of temperature. The thermal radiation between the active wall and the cavity surfaces also increases with the Rayleigh number, but less rapidly than the convective heat transfer. As for the total Nusselt number, it also increases with the Rayleigh number. Therefore, the higher this parameter is, the more the active wall is cooled. This figure shows the streamlines and isotherms obtained for different emissivities, keeping the Rayleigh number at 10 power 6. The streamlines are very dense near the active and upper adiabatic walls, indicating a very strong velocity gradient at this location. Such a density remains almost unchanged by increasing the emissivity. In other words, the flow structure is insensitive to surface radiation for high Rayleigh numbers. The isotherms show that the thickness of this thermal boundary layer increases with emissivity. As a result, the cold fluid volume in the cavity decreases. Figure 5 presents the variations of the mean convective, radiative and total Nusselt numbers on the active wall against the emissivity. It shows that the mean convective heat transfer linearly decreases with this parameter. In contrast, the radiative heat transfer is an increasing function of the emissivity. Such an increase is also almost linear. As for the total heat transfer, figure 5 shows that it increases with the emissivity, although the attenuation of the convective heat transfer. In other words, increasing the emissivity promotes the cooling of the active wall. In conclusion, we can retain the following points. The Rayleigh number has a significant effect on the velocity and temperature fields. However, the emissivity has practically no impact on the flow structure for high Rayleigh numbers, but it remarkably affects the isotherms. Numerical simulations performed also show that increasing the Rayleigh number leads to an increase in the convective, radiative and total heat transfer, while for the emissivity, its increase leads to an important increase in the radiative flux and a slight decrease in the convective one, and consequently an increase in the total heat flux extracted from the active wall. And thank you for your attention.